I'm excited to present today about the research and development behind this kind of multi-purpose climbing space bots for Mars, Moon, and space. And so we'll be focused more on the research side of these robotic systems and their implications and applications. So here are some challenges to assembling and maintaining the ISS. So we know that it's around 1,000 hours for extra vehicle activity hours to assemble and maintain the ISS with handholds and tethers. So there's a lot of maintenance involved, and these human EVAs have traditionally been performed to install new components such as solar and radiator panels, tanks, rewiring systems, modules, sensors, cameras, batteries, and all sorts of equipment, and also to monitor, install, and retrieve scientific experiments, and then astronauts train around 7 hours in the pool for every 1 hour during their EVA to prepare. And so we can begin to envision how other systems and robotics might be able to help alleviate some of these time and cost burdens. And here on the bottom right is an image of the Canadarm 2 that's currently on the ISS. It's 17 meters long, and so we can begin to envision, what would this look like on a spacecraft or starship or rocket, later on in the future, and how can we design this to be more kind of multi-purpose oriented, and with greater mobility and maneuverability. And so here are some of the challenges toward space robotics and operations beyond Earth and specifically on the Martian surface. We have this extreme environment, extreme temperature fluctuations, and then we have these dust, all this dust and storms, and so for astronauts also prepare for 2 to 3 hours per day for 2 weeks of preparation on board the ISS, and so this is around it, and then that's followed by another 6.3 hours on average per EVA, and then we also have this time delay, but these difficult to access locations on spacecraft and rockets and habitats really impose some challenges toward the expansion and settlement of Mars and the Moon. And so traditionally we've been limited to kind of horizontal settlement expansion to some extent, theoretically, and as the settlement scales. See some people in the waiting room here. They're in. I have to stop sharing. Well, I hope they got in, but okay, coming back. All right. So as the settlement scales, this kind of vertical expansion becomes increasingly attractive. And all these challenges and factors, they help necessitate the need and the guidance of autonomous robotics, and in particular climbing robots that can move horizontally, vertically, and in many directions. Let's see, they're at the top here. Okay. Here we go. So here are some examples of climbing robots. There's the city climber here that's inverted and can walk on ceilings with a 4.2 kilogram payload and operate on rough surfaces. Here's the Meko Gecko. It has three legs here, the robotic system. And hey, Abhishek, we can hear you there in the background. If you can mute, that would be wonderful. So this they're pressure sensitive adhesive bindings that mimic the unroll and peel off manner of how the gecko climbs, and so through these really tiny microscopic angled hairs on their feet that generate these van der Waal forces to create this stickiness attraction. And here's NASA's Lemur. It scales cliffs with this similar gecko design of fish hook grippers. And here's Rise, the amazing climbing robot that uses electrostatic forces to bind and climb vertically with these, and similar to the SRI static electric wall climbing robot here as well. And here's some examples of robots for glass window and cleaning. There's a Hubot magnetic climbing robot that's much more smaller scale, and the window shade here as well, and this other Amy glass robot here, and so we can envision how we could take these systems with us as we expand beyond Earth and to Mars and elsewhere. And this was really interesting too. Here's a bunch of designs of these wall climbing robots that with flying ability, and it's really unique. And I think these become much more. They hold great potential in reduced alternative gravity and on Mars. And so I think, yeah, we'll have to brainstorm on this one and what kind of applications and ideas might make the most sense. And then here are the unable to fly wall climbing robots from the same publication here. And I found this one really interesting as well. This is the MINOAS, the Marine Inspection Robotic Assistant system. It's a magnetic crawler with a flexible tail that actually significantly improves the maneuverability from this tail here on the end, enabling it to climb vertical walls along that was primarily designed for large cargo tanks and marine vessels in particular. So they're on 50 neodymium magnets per wheel, and it's really interesting how they use this attraction to increase the adhesive power and orient the magnets in an opposite magnetic field orientation to really climb over all sorts of pipe bends, sharp obstacles, and joints. And so I don't believe that the steel alloy with the Starship will be capable of attracting these magnetic forces, but perhaps on other systems and structures, there may be some application. And so here are some other multi-purpose applications of these climbing robots on these planetary surfaces, and in particular on how we can really enable the settlement of Mars, help anchor cables in the bedrocks, and help install the equipment for deployment. They can enable the attachment, imaging, and guiding of hooks and end effectors with cranes to help construct systems and habitats, and with these end effectors, they can weld and manufacture systems and metals together, and even help install communication and antennas, and then help repair and maintain them on spacecraft and habitats and structures, and collect data and imagery for spectroscopy and maintenance as well, of all sorts of systems. And they could also even help inspect heat shields and perform maintenance on other larger scale structures. And so here's some other multi-purpose applications. Imagine one day, they could be used to help inspect and maintain materials and high altitude balloon platforms. They could assist with on-orbit assembly, maintenance, and EVAs. But really, I feel like they could enable vertical building, construction, maintenance, and expansion as well, which is where there's some of the most potential, as well as really helping anchor into canyon walls, and helping build out settlements inside canyons, and enabling the vertical transportation. But then also provide humans and cargo with low mass transportation, in addition to the dust cleaning and applying coatings on all sorts of locations that are in more hard to access locations. And they can be used to build and maintain domes. There's all sorts of designs to consider. And I feel like we've discussed a bit about this concept as well, and I think it holds incredible potential to use these cables as a deployment system from Starship, but also they could help enable the Starship to be horizontally aligned and deployed to the Martian surface, and possibly even establish a canopy or hangar, and assist with the deployment of the domes. But so these cables would have much less forces in these reduced gravity, and so then we can also we can transmit electricity as well through these cables, and tethers, and so they really enable construction and modifications on spacecraft and habitats. We can envision these kind of cable climbing robots, and here on the right here is a diagram of how we could use these climbing space bots on the surface of spacecraft and Starship, and via a tethered system anchored in from the top. And that system could rotate, or it could be attached to a loop, and so then we could almost have like a near 360-degree axis to the entire exterior surface of the spacecraft for all sorts of maintenance and installation of systems and components, and so we could really recover a lot of time and cost during EVAs, and they could also help with these climbers. They could have these mechanical grippers with wheeled brakes, and so a lot of times with this mode of transportation, the Coriolis force really limits their the climbing velocity here, and here we've outlined a lot of the material properties and strength for various cables. But they're really nice way to, in good TLR demonstrator for space elevators. Even I feel like, interconnecting, high altitude platforms and habitats in the Venetian atmosphere. And um, uh, yeah. So one of the last slides here. So with a variety of these end effector designs, there's a myriad of applications that become possible. And so here we've outlined five of them here. These end effectors could be attached to the central hub of these space spots and enable drilling and fastening, and some effectors could be designed with grippers and fingers, and other effectors could help apply sealants, paints, and coatings to all sorts of materials and surfaces. It can also help laser scan and weld with torches for horizontal and vertical welding, and then measure the holes, and analyze holes after drilling, and all sorts of needs for what we need holes for to help enable construction. And so with the right effector and body designs, I feel like this space spot could really climb up horizontally aligned starships for laser cutting as well, and weld vertical pipes together and so many things. But so I feel like there's a lot of untapped potential with the vertical movement in reduced gravity, and especially on the moon, but also on Mars. And so here's one of the aims of what we're doing with this research project. We're aiming to design and build a lightweight, multi-purpose, electrically powered robot for assembly, construction, maintenance on the moon, Mars, and for transit. With swarms of multiple miniaturized and macro robotic end effectors that really help enable these applications. So here we've outlined some of the components for navigation, electronics, communication, and payload. And I feel like we could help inspire the design of what the researchers here did with the 3D printing B1M robot builders, and help really bring more effective designs to enable really the more far-term settlement expansion. So yeah, I think that's just about it for my presentation here. I think yeah, we're really these parts and effectors should be universal and adaptable, to most other robotic systems, and both fixed linear systems and nonlinear and in motion too, so that they can be used across all sorts of robots in unison and collaboration. I feel like we can accomplish so much and have all sorts of fun with a variety of these robotic systems and effectors. And so that's it for my presentation. Thanks for listening. Thanks.
Hey, Cole. It's Terry Recker. Are you familiar with a company called Off-World Incorporated? It's out here next to JPL in LA. If not, then I recommend getting in touch with James Cavalli, and I'll put his email in the chat. But the last project that you just spoke about goes in line with a lot of what they're doing. And they're talking about off-world manufacturing, off-world mining, reconfigurable artificial intelligence, robotics. But that might be of interest. Do some work together, collaborate together with him.
Thanks, Terry. Yes, Jim is it's impressive to see what they're doing. So yes, should reach out.
space around the world opposing you. Different parts of the left took a different attitude.
It's a little difficult to hear you trying to speak to us, but if no one has any further questions, we can go ahead and jump into the next speaker.
I have a question, Cole. I'm sorry. My name is Tishan. In listening to what Charles was talking about earlier of having access to some of the elements, how would that impact utilization of the robots?
Yeah, that's really great question. Some sort of data integration and in particular for mining, I feel like.
Can I chime in here, Paul?
Yeah, you could probably answer better.
Yeah, it's a great question, Tishan. Thank you. I was just going to say, I guess what would be interesting is to have a collaboration between the roboticists and the microbiologists to actually make the robots out of the elements that are most easily mined by microbes or plants or whatever you use to do the mining, rather than just in designing these robots in isolation and assuming that the elements you'll get access to somehow, but actually to use types of metals that can be easily extracted on Mars. Cool.
Thank you.
Second that, and really interested to see what we could design with what sort of end effectors we could design to help enable the biomining.
Yeah. I have a quick question then, Colin. Would you imagine a factory producing a large number of these on Mars so they become, as you say, all purpose? They're being used for as many different activities as possible. So you've sort of got plug and play pieces you put onto them.
Yes, exactly. Yeah, I think I think a pressurized warehouse and storage area makes a lot of sense, where we can store a lot of these parts and then combine them and put them together, and then also charge a lot of systems and robotics, and also design and manufacturing. Yeah.
But any pressurized facility outside the Earth's atmosphere is going to be costly, especially if you start talking about 14.7 psi, which is what we live at right now. So it would have to be a good trade-off between available resources, power, assumption and generation, and overall need of the equipment systems. So it's pretty costly outside the Earth's atmosphere to generate such a big system or a big need.
Yeah, it's a great point, Terry. I feel like one of the main drivers to make it pressurized is to have that human interaction with the systems and robots.
But the key should be to make them as autonomous as possible. The only time that I would see having to have human need is when it's absolutely necessary, because touch labor is extremely expensive as well. And so it becomes one of those kind of things. And I put a comment in the chat that the next generation artificial intelligence is what we're really working for right now. And that is that cognitive self-awareness, decision-making artificial intelligence that would lead each one of the robotic elements to form a collective. So that touch labor is expensive.